So, hello everyone, how are you all? I hope you all are fine and safe. Well, again, welcome back to Quantum Mathematics. I'm Aman, just welcoming you all to a new amazing video in which we are going to talk about a thing actually which we are using continuously, but we don't know the proof of that yet, right? So I think it's time to just prove that down. And you know what? What is that? It's this one, pi z times cotangent of pi z equals 1 minus 2 times the sum as n goes from 1 to infinity of Riemann zeta of 2n times z to the 2n, right? So basically, yeah, this equation, we are using this equation like continuously, I would say. I have used this in my most recent video. You can check that out, and I would request you to check that out because that's really crazy and amazing video, like literally. Yeah. So now let's talk about the proof of this. And you know what? Again, from the thing that we have proved in our previously we have proved that. So basically, we have proved this previously, and we are going to use that. What's that? It's pi times cotangent of pi z equals 1 over z plus the sum as n goes from 1 to infinity of 1 over z plus n plus 1 over z minus n. So yeah, if you are a daily viewer of my channel, so you have encountered this for sure, right? So basically we are going to use this result, and I have proved this. I will paste the link of the proof of this thing in my description box of this video. Don't worry about that. We are going to just prove this down from here, right? So let's just dive into it. And it's extremely amazing because you know what, just take a look at here. It's something like some algebraic terms, but here I'm having some Riemann zeta, so it's kind of weird, right? But it's all right. Let's prove this down, and it's really amazing. So first of all, we can see on the right hand side there are some changes here. If I talk about both of the expressions, so in this expression actually, let's multiply both sides by z, right? Okay, so that's gonna give us pi z cotangent of pi z, right, on the right hand side. And on the left hand side we would be having z times 1 over z plus the sum as n goes from 1 to infinity of, well, we can just write this as z plus n times z minus n, right? And we have to just take care about the numerator as well. So that's gonna be z minus n plus z plus n. So this minus n plus 1, I'm sorry, plus n is gonna canceling out each other. And yeah, so far we are having that much things. And now pi z cotangent of pi z equals, so I'm just gonna multiply this z to these two expressions, right? So when we talk about z times 1 over z, it's gonna be 1 obviously, and it's gonna be z times the sum as n goes from 1 to infinity. And here we got rid of n, so, and we are having z plus z, which is 2z, right? So 2z over, and here we are having z plus n times z minus n, so it's z squared minus n squared. Yeah, it's fine, right? Okay, so our pi z cotangent of pi z, the right hand side as it is, I'm sorry, left hand side. Oh, I think I'm just messing up with right hand side and left hand side. I'm getting confused. If I have said this side as right, left hand side, I'm really sorry about that, guys. I'm apologizing. I'm apologizing for that. Okay, it's all right. We are made for mistakes. So we can just multiply this z to this one, so that's gonna give us 1 plus this sum as n goes from 1 to infinity, and it's 2z squared over z squared minus n squared. Although we can just let's just write this down as n squared minus z squared, and to neutralize that we have to multiply here a negative in front, and this plus minus is gonna be negative. Actually, I hope you guys are not getting confused in order to do that, right? Just if you want to check this again, so this is z squared minus n squared, and it's n squared minus z squared, and here we are having negative, and if we talk about if we're gonna multiply this in the denominator, so we're gonna have the same result that we had earlier. Okay, and again pi z cotangent of pi z. Here we can just do some great manipulations here actually. And why we did that actually, what's the reason of why we did that, so I'm just gonna tell you that, don't worry. So let's just plug 2 common out here actually, because it's a constant, right? So yeah, and it's z squared over taking n squared common as, right? Like I'm just factoring out n squared from the denominator. So I'm just gonna have 1 here, and here we're gonna get like we're gonna have z squared over n squared, right? Just take a look when you multiply this inside this parenthesis, so that's gonna give us, I'm sorry, it's n squared minus z squared times n squared over n squared. So n squared cancels out, and we would be having n squared minus z squared. That's it, right? And why we did that again, don't worry, let me just show you a beauty here. In order to just convert this into some Riemann zeta things, right? 1 minus 2 times the sum as n goes from 1 to infinity, and it's z squared over n squared, and it's 1 over 1 minus z squared over n squared. And now let's just talk about this thing actually, and this is pretty amazing, because yeah, well, we know that we can represent 1 over 1 minus x as the sum as n goes from 0, or maybe let's consider k, right, instead of 0. K goes from 0 to infinity of x to the k, right? And the condition for this is the absolute value of x should be less than 1. And this is pretty amazing thing, because you can just represent any I would say some denominator stuffs as an infinite sum if you're having something sort of this. Wow, that's pretty amazing. It's basically it's an infinite geometric sum, right? Infinite geometric sum, right? Okay, so for our case we are having 1 over 1 minus z squared over n squared. So our x is z squared over n squared here, right? Just you can compare that. So basically 1 over 1 minus z squared over n squared can also be written as the sum as k goes from 0 to infinity of z squared over n squared whole to the k, right? Yep, that's cool. And now we can successfully represent this, I think this one, with this infinite sum, right? Let's just do that. So basically we are having pi z cotangent of pi z equals 1 minus 2 times the sum as n goes from 1 to infinity of z squared over n squared, and times the another sum as k goes from 0 to infinity of z to the 2k over n to the 2k, right? We can do that. We just had splitted the exponents here, right? Okay, so now we can just represent it as a double sum here. Pi z cotangent pi z equals 1 minus 2 times the sum as k goes from 0, because due to linearity we can just switch up the order of like index variables with k, the sum with index variables and with k, and it's the sum as n goes from 1 to infinity of it's z to the 2k plus 2 over n to the 2k plus 2, right? Okay, and here pi z cotangent of pi z comes out to be 1 minus 2 times the sum as k goes from 0 to infinity. Well, let me just show you this clearly. N goes from 1 to infinity of 1 over n to the 2k plus 2, and it's z to the 2k plus 2, right? Okay, and now we know the Riemann zeta function definition. What's that? Riemann zeta function. So basically it says that the Riemann zeta of, oh, I think I should just, Riemann zeta of s is the sum as n goes from 1 to infinity of 1 over n to the s. So this is what Riemann zeta of s is all about. So for our case, we are having s equals 2k plus 2. Just take a look at these two things. If we compare this s with this one, so it's basically this sum is representing Riemann zeta of 2k plus 2, right? Okay, so our pi z cotangent of pi z, wait a second, coming out to be 1 minus 2 times this sum with index variable k, right, from 0 to infinity of Riemann zeta of 2k plus 2 and z to the 2k plus 2. And now let's just plug 2 common out of both the argument of Riemann zeta function as well as the exponents of z from the right hand side. Pi z cotangent of pi z 1 minus 2 times this sum as, wait a second, k goes from 0 to infinity. Yeah, now it's quite good looking, and it's Riemann zeta, wait a second, Riemann zeta of 2 times k plus 1, and it's z to the 2 k plus 1 as well. And now we can just put here, let k plus 1 equals n. So when k is beginning from when k here is 0, so n is 1, it means the sum is gonna begin from 1, right? So hence we are here with our final result, pi z cotangent of pi z 1 equals 1 minus 2 times this sum as n goes from 1 to infinity of Riemann zeta, wait a second, Riemann zeta of 2n and z to the 2n. Here it is, guys. Wasn't that amazing? Like literally we didn't use any extraordinary stuffs here. We just did some manipulations and we are here with our final result. We know about the definition of the Riemann zeta function here, and although we did this one, like we did use of the infinite geometric sum, and that is why we just got reached up to Riemann zeta function in an unexpectedly result, like out of nowhere, I would say. Like reaching from here to this, isn't it quite weird? But it's all right. Mathematics is not weird, it is magical. So yeah, I think it was literally amazing, and it was prerequisite, I would say. And I'll paste the link of the proof of this one, so don't worry about that. But for now, let's just take leave here. And again, guys, if you got to learn something from this video, please make sure to like, subscribe and share. And if you have any kind of doubt so far, you are free to ask me in the comment section. I'll be there to reply your questions anytime, right? So yeah, just learn mathematics because it's really amazing. Don't study mathematics, learn mathematics, dive into it. Oh my goodness. Okay, goodbye guys, take care, love you, and be careful.